Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your main topic, that is integration. Under the aspect of it, that is application of integration, where we started to learn how to find the area under the curve. Today, we are going to take the second case, and that second case is area between the curve and the linear equation y equals to mx plus c. So let's begin. After completing the very lesson today, my dear student will be able to find the area between the curve and the line y equals to mx plus c. This is what I hope you'll be able to do after completing the very lesson today. So as usually in your favorite segment of the lesson, Marcy Stefan, today I want to tell you this number 9 is somehow hidden in your geometry. I will explain how this number 9 is hidden in your geometry after completing my lesson today, so don't go away. My dear student, in our previous lesson, you learned how to find the area between the curve and the x-axis. In this very lesson, we are going to take the other part of it, that is the area between the curve and another straight line y equals to mx plus c. So let's begin. So to find the area, let's just consider a general curve y2 equals to f of x. This is the curve, and you have the general straight line equation y1 equals to mx plus c. So y1 is the straight line while y2 is your curve, as you can see displayed here in this very drawing. You have the curve y2 equals to f of x. Look at the curve, and this is the straight line equation y1 equals to mx plus c. And this is the area A between this curve and this straight line. It is this area that you learn how to find or how to determine the area of this very portion, this very region. So the area between this curve y2 and the straight line y1 will now be given by this simple formula. This is the formula. It says the area A will now be equals to, or will now be given by this definite integral from A to B of y2. Remember, y2 is your curve and y1 is your straight line of y2 minus y1 with respect to x. So you simply replaced your function y2, that is your curve, minus your straight line equation, that is y1. That simplified the form. You now find the integral. And when you find the integral function, you now substitute those limits. It will now give you the area. So this is the simple formula we now used to find the area between the curve and a straight line y1 equals to mx plus c. Where those limits a and b, that is a and b, are the points of intersection of the curve and the line. So where the line and the curve crosses each other, the value of x at those points, as you can see in this very drawing, the curve and the straight line intersect here, and at this very point, if I come down to the x-axis, it will give me my a, and they also intersect here. That is the curve and the straight line, they crosses each other at this very point, and if I move to my x-axis, it will give me the value b. So where the two, that is the points of intersection, the 2 points of intersection now gives you the value of x at those points, will now give you the limits. So the smaller one will now be your lower limit, and the higher one will now be your higher limit. We are going to take examples how we can make use of this rule to find the area between a curve and a straight line. Let me just move and take an example. Example number 1, it says find the area between the curve y equals to x squared and a straight line y equals to 3x. Solution to this very problem, what we do first is to write down the rule. The rule says the area between the curve and a straight line is given by this formula, and this formula says the definite integral from a to b of y2, where y2 is your curve, minus y1, which is your straight line, and that simplified form, you now find it is integral with respect to x. So let us move. So what I'm now going to do is to now find the limits. The limits, this a and the b, those limits a and the b, the rule says is now the points of intersection of the curve and the straight line, the value of x at those points of intersection will now give you the limits. So to find the point of intersection, what I'm going to do is to now take this my curve equated with the straight line and solve that very equation. So solving x squared, that is my curve, equals to 3x, that is my straight line equation, where the two crosses each other, this always hold. That is, the value of y at those points will now be the same. So solving this very equation, what I'm going to do is to take this 3x to the left hand side. There gives you x squared minus 3x equals to 0. So I'm going to solve this very quadratic by factorization. So I can factor x from this left hand side. X is common. That will give me x into x minus 3 equals to 0. So I'm having x times this bracket and the result is 0. So surely either this x is 0 or this bracket is 0. Or whichever the case is, you now take both cases. So x is now going to be 0. If it were the bracket that is 0, then x is now going to be 3. So this now is the solution of this very equation, x squared equals to 3x. And this will now serve as my limits of this definite integral. This x0 is now the smaller one, so that will now be my lower limit, and the 3 will now be going to be my higher limit. So I'm going to have the definite integral from 0 to 3 of y2. Y2 is your x squared, and y1 is 3x. So I'm going to have the definite integral of x squared minus 3x with respect to x. So I'll continue. So I'll now find the integral. Integral of x squared, that will be x2 cubed divided by 3. And the integral of 3x, that will now be 3x squared all over 2. Let me just write it. This is the integral. For the x squared is x2 cubed all over 3 minus this subtraction. And the integral of 3x is now going to be 3x squared all over 2. Then plus the constant of integration c. And these are just my limits, 0 and 3. So I'm going to replace the x by those limits, starting with the higher limit, which is 3. So let me do that. So I'm going to have 3 raised to the power of 3. I have replaced this x by this higher limit over 3 minus 3x squared. So instead x, I now have a 3 there. So I'm going to have 3 times 3 squared all over 2 minus, that is, I'm now going to substitute the lower limit in here. So I'm going to have 0 raised to the power of 3 all over 3 minus 3 times 0 square all over 2. I'll continue. So I'm now going to simplify each of this part here. This is 3 raised to the power of 3, which gives 27 over 3. And this 3 square is 9 times this 3 outside, gives me another 27 over 2. So I have 27 over 3 minus 27 over 2. So using LCM to do that subtraction, LCM of 3 and 2, which will now be 6. So if you do that correctly, you're now going to have minus the 27 over 6 as the result of this very part. And this second part, 0 raised to 3 is 0. 0 square is also 0. So in the end, this part will be 0. So we are now subtracting 0. So this is now the result of this very first part, which is now negative 27 over 6. And if you now divide 27 by 6 and disregard this negative sign because area will not be negative, so you're now going to have you are now going to have 4.5 square units as the area between this very curve and the straight line y equals to 3x. With these few examples, I hope you'll be able to find the area between the curve and the line y equals to mx plus c. This is where I'm going to stop in this very lesson, my dear student. Let me just move to the last part of it, that is maths is fun. In geometry, this very 9 is hidden in so many places. Let us see how this number 9 is hidden in your geometry. If you take a cycle has a total angle of 360 degrees. And this digits there in 360, that is 36 and 0. If you added them together, let's see what we are going to have. 3 plus 6 is 9, 9 plus 0 is still a 9. So adding this 3 digits in 360 degrees, that is total angle in a cycle, gives me this very number 9. So I will now divide this my cycle into half. That is divided by 2 equally. So if I divide my cycle into half, that is I'm going to have a semi-cycle. And angle in a semi-cycle is now 180. Let me add those 3 digits in 180. That is 1 plus 8 plus 0. Let me see. It's still giving me 9. 1 plus 8 is 9. 9 plus 0, it will give me 9. So let me divide my original cycle into 4 parts equally. So dividing the cycle into quarter, that is 1 over 4 of 8. So each piece will now have an angle 90 degrees. It's just dividing 360 by 4. So each angle of that very quadrant, that is one piece, if you divide it into 4, one piece will now have an angle 90 degrees. And if you add those 2 digits there in 99 plus 0, it will still give you 9. You can see this very 9 is very hidden in these angles in your geometry. Let me divide my cycle into 80 parts equally. So dividing the cycle into 80 parts, each one piece will now have an angle 45 degrees. 45 degrees is just to obtain dividing 360 by 8, it will give you 45. And if you add those two digits, 4 and 5, you still have the same number 9. This is really interesting. Let me divide my cycle into 16 parts now. So dividing the cycle into 16 parts, each part will now have an angle at the center 22.5 degrees. That is 360 divided by 16. This is what you are going to have. And if you add those 3 digits, 2, 2, and 5 also, I expect you get this same number 9. Let me just finally divide my cycle into 32 parts. Into 32 parts, each part will now have an angle 11.25 degrees. And adding those 4 digits, 1, 1, 2, 5, also if you did correctly, you still have the same number 9, which means this 9 is somehow buried inside this your geometry, which I believe you never noticed. So we see more of this amazing things in mathematics in our subsequent lesson. Thank you for your attention.